Hello, my name's Doug Arian, and I'm the head of the Mountains of Stars program, and for many years been on the faculty of Carthage College. Welcome to this talk, which is part of the joint effort between Carthage, the Appalachian Mountain Club, and many other academic partners. The goal in our program is to connect you with the biggest of big pictures and hopefully change the way you look at things by understanding where we came from when we look at the universe as a whole. This talk is entitled, Are We Alone? It's a very interesting question to think about life elsewhere in the universe and whether we are the only life out there in the universe. And a lot of recent events give us even more reason to consider this. We can start out by thinking about all the different kinds of life that we have on Earth. Humans are just one kind. In fact, mammals are just one kind. Here you see Shadow the cat. He's sitting on the ottoman here napping while I'm recording this webinar for you. But, mammals haven't been here that long. Insects, there are way more insects than there are people. In fact, there's more plant life than there is animal life when you think about it. If you look out and think about how many blades of grass or trees are out there. Think about everything that's under the water. 70% of the planet is covered by water. And all those creatures look very different from us. Reptiles and amphibians, they're a whole other class. Bacteria, they go back, of course, to the beginnings of life on the planet, many kinds of them. And today, of course, viruses are particularly interesting. This is COVID here, of course, and they're a whole other type of thing. They're based on RNA and DNA just like we are, but they're just a chunk of genetic material surrounded by proteins. We don't even really know where they came from, whether they evolved the same time as other kinds of life, before them or after them. So that's a whole other kind of thing to be considering. And these, of course, are the kinds of life that are on the planet today. Through history, there have been all sorts of other things. Dinosaurs, of course, they were here for a very long time. The huge megafauna that were throughout North America, all of which are gone now. Ferns, if you like ferns, you realize that they're primordial. They go back to very early plant life on the planet. They were here while the dinosaurs were here, and they reproduce through spores. They do something completely different than other plants. And then there are other kinds of life that we know only through fossils. This is a fossil of crinoids. We don't have them anymore today, but we know that they were there because we have the fossil evidence. And of course, we're interested in people and humans. And, there's kind of an assumption that if we're looking for life in the universe, the most important kind of life that we can find is Star Trek, of course. Things that speak English, Romulan, Klingon, or Vulcan, they look a lot like us. They stand upright. They have 2 eyes, 2 ears, a nose, and a mouth. And, it's kind of like, if that's the important kind of life, that's what we're looking for. Now, the question is, what kind of life is out there? Could there be life out there? And we have to realize that there are a lot of opportunities for it. We look out there, and it's kind of hard to believe that in all of that's out in the universe, that the Earth is the only place that life formed. But so far, we don't have any evidence for it. But we'll talk about that in the next few minutes. Now, if we'd like to try to understand life, it's important to understand where the building blocks came from. So early in the universe was only energy, and as that energy condensed to form stuff, it really only formed a couple of kinds of stuff. 3/4 of everything that was formed at the beginning was hydrogen, and hydrogen has one big particle in it, one proton. 1/4 of the material is helium, and helium is unique because it has 4 particles. And there's a tiny smidgen of lithium that's generated. Those are the only ingredients that you have. So you can't have people early in the universe. You can't have planets early in the universe because you don't have the building blocks to make it. It's as if you go to your cabinet and you're going to cook and you find, a big bucket of flour, maybe a tiny little vial of salt and 3 peppercorns. That's it. That's all you get to play with. So you can't make much with that. Now, where did we get all the parts and materials to make you and me and everything that's out there? Well, that's made in stars. When you look up and you see those pinpoints at night, each of those pinpoints is a giant ball of gas. The sun is one of them. The sun is one of the smaller ones, as a matter of fact. And the way stars work is these giant balls of gas are so big that just the weight of the gas alone compresses the cores to incredibly high temperatures and pressures. And at those temperatures and pressures, these atoms hit each other and stick. So hydrogen atoms hit each other and stick to form heavier things. Helium atoms stick together and form heavier things. And it's very important to realize that with hydrogen, you have only a single particle. So as you build things with hydrogen, you can add one at a time. 1 plus 1 plus 1 plus 1. So imagine building a building where you have to do it with individual 2x4s. So you put one up, then you go back to the store and get another one, put another one up, go back to the store, get another one, put another one up. You can do that, but you can imagine it's a very slow process. Now the thing is, you have helium. Helium has 4, so you can build things that have 4 parts at the same time. So it's like buying a roof truss. You can put on a whole roof truss, then you can put on a whole nother roof truss. So you build things more quickly. So over the lifetime of a star, which is millions to billions of years, at the core, heavier and heavier elements get built. The heavier ones near the center, lighter ones in shells around that. The thing is, this process only builds elements up to iron. Iron is so big and stable, we can't smack more things together, even with the complete weight of a star pushing on it, to make heavier elements. And yet, iron is only a third of the way through all the elements. We're missing 2/3 of the elements. The rest of the elements are made when objects collide or when very big stars, stars that happen to be born large, end their lives in explosions. These are called supernovas. And the image you see on the right there is an example of our best picture of what one of those explosions look like just after it's happened. That process happens very rapidly. So the oxygen that you're breathing right now was born inside of a star, and it took millions to billions of years to cook up all the oxygen that you have for breathing. Yet, if you're wearing any gold, silver, or platinum jewelry, that was made in 2.5 seconds in an exploding star. Same with all the radioactive elements that power our power plants. All these different elements were made through the lives and deaths of stars. And so we have a really good understanding of where all the elements came from. As you can see here in the blue, all the hydrogen, most of the helium, a smidgen of lithium, yeah, it's from the Big Bang. But every other element here was created during the lifetime or at the death of a star. Now, they're not all made equally. The fact is that we have helium, which is a multiple of 4. And so if we look at how much of each element there is in the entire universe, we find that the ones that are multiples of 4 are more common than any others. And in particular, as you can see here, we have lots of hydrogen and helium. The next 2 most common are carbon and oxygen. What you have to realize is each little tick mark on this graph means you have 10 times as much as one tick mark below it. So actually, there's a lot of carbon and oxygen compared to everything else. You'll also notice all the other elements here that are more common than others. Now here's a really cool thing. If you combine carbon and oxygen with a lot of the hydrogen that's around, you make something really, really important, which is sugar. And sugar is the basis of all life on this planet. Everything on this planet either eats it to have energy or makes it. Plants and bacteria make it. You and I and all the other kinds of life here eat it, and that's what powers you. That's what gives you all the energy to do things. The reason that sugars dominate life, and in fact why we have our kinds of life at all, are related to the fact that stars are better at putting multiples of 4 together than anything else, and the fact that they make carbon and oxygen more than everything else combined. That is what leads to the life that's here. As you start with sugars and you add in more and more sugars and more compounds, you start to make things like DNA. So DNA is a consequence of the fact that stars are better at making carbon and oxygen than anything else as well. Now, if you also look at the very common elements here, you're going to discover that there are 4 others that are very, very prominent. In fact, besides oxygen, there's also silicon, magnesium, and iron. And believe it or not, those 4 elements form all of the rock on the Earth. So if you look at the whole Earth, the entirety of it, not just a little bit of the surface that we can see, the fact that we're a rocky planet is a consequence of the fact that stars are better at making multiples of 4 than anything else. And multiples of 4, let's see, oxygen, I already told you, is 4 times 4. Carbon was 3 times 4. Magnesium is 5 times 4. Silicon is 7 times 4. And iron is 14 times 4. So these factors of 4 are critically important because they make the compounds that produce life for us, the sugars, and that produces rock. Now, that also tells you something about looking at the universe as a whole, because all stars behave the same way. They're producing elements in the same way. You expect to find the building blocks of sugars all over the universe. You expect to find carbon compounds all over the universe. And you expect to find rock everywhere. And rock, of course, is very important to our kinds of life because we can't stand on gassy planets. We can only stand on rocky planets. So if we're looking like our kind of life and we're looking at things that are on rock, the fact that stars make silicon and magnesium and iron and oxygen indicates that we're probably going to find rock in lots of places in the universe. Now the processes look something like this. On the left, that sort of pinkish glow, well, that's the thing nicknamed the Crab Nebula, and it's the result of a star that exploded. So that's a very dirty cloud. It has all 92 natural elements in it. And we know that because that star lived its lifetime, so it bred elements up to iron. When it exploded as a supernova, it bred all the other elements. So this cloud has all 92 elements. You can think about it as the ultimate supermarket. It's like a super Walmart or Amazon. Whatever you want, it's available there. Now the object on the right is more like what will happen when a small star, a star not big enough to explode, ends its life. So the sun will do something like this in about 5 billion years. The core is that little dot at the center, and that's left there, but the rest of the star floats off into space, is pushed off, and that contains all the elements that star bred during its lifetime. But remember, since this star didn't explode, it only has elements up to iron. So lots and lots of lighter elements, no heavier elements. And this shows up throughout the universe. So when we see these beautiful gas clouds, the one on the left is nicknamed the North America Nebula. Perhaps you can recognize North America there. The reason the clouds have these shapes is not just because that's where the gas is, but those dark streaks that run through it are not an absence of gas and stars. It's actually clouds of what we call dust, carbon compounds, heavy carbon, organic kinds of molecules, and little rock particles floating through space that block the light. So you see where the dark areas are. You don't see the stars in the background because those dark areas are in the foreground. In fact, our galaxy, the Milky Way, which you can see at the upper right, and if you've ever been to a dark sky, and we'll talk about that before we're done today, that big streak that goes through the middle of the Milky Way that's dark is not an absence of stars. That's a big cloud of this dusty material throughout. And every other galaxy has things like this too. Another galaxy you can see at the lower right there, and that band of dark material is also organic. So we now know that throughout the universe, in all these places, the building blocks of our kind of life, carbon, hydrogen, oxygen, nitrogen, rocky materials, are all very, very common. So let me tell you a little story. Once upon a time, 5 to 8 billion years ago, at least one of those big fat stars exploded, and at least 2 or 3 smaller stars ended their lives. During their lifetimes and at their deaths, they created this collection of elements. That gas spread through space, eventually condensed into forming a new cloud. Gravity pulls on everything, and that new cloud, new baby stars formed. One of those baby stars turned out to be the sun. And the debris left from forming the sun formed the planets around the sun, including us. We have just the right mix of elements. If those stars hadn't lived and died in exactly the right place at the right time, we wouldn't have the right mix of elements. We need just enough of the lighter elements, that silicon, that magnesium, the oxygen, the carbon, to create the life conditions for us, and just enough of the heavy elements to keep the planet hot, create the geology that we have. If you had too much of one, not enough of another, lo and behold, our kind of life wouldn't be here. So it's quite spectacular to think about the circumstances that had to come together out in the universe to put just the right mix of elements together in this place so that you and I can be here. Now, there's some other things that had to happen to put our kind of life on the planet. Let's consider the following. So, when planets form, they form either very rocky, and that's with heavier elements, relatively speaking, closer into a star, and farther out, you end up with the lighter elements. So, all the planets in our solar system form into two categories. The one nearby are rocky, Mercury, Venus, Earth, and Mars, and the ones farther out are all gassy, Jupiter, Saturn, Uranus, and Neptune. So, we need to live on a rocky planet, and we do, so that means we need to be one of the inner planets. All the gassy planets have lots and lots of moons. Jupiter has 79, Saturn has 82, Uranus has 34, huge families. The rocky planets, however, are a little different. So Mercury has no moons, Venus has no moons, Mars has two little captured asteroids. In fact, when you get rocky planets, you tend not to get moons, and yet we have a huge moon. The Earth and Moon are really a double planet. We would be one of the sexiest things in the sky if amateur astronomers elsewhere were looking at us. Now, we have that because early on, when things were still floating around in the solar system as it formed, the blob that became the Earth got whacked into by something roughly the size of Mars, and it spat out a chunk of material that became the Moon. That's a, if you wish, random collision that made this happen. Not very likely thing, but it happened. Okay, so you used to think that the moon was normal, I guess. Guess what? It's not. It's pretty rare. It's pretty odd, especially to have a satellite that's that huge. Now, what does that have to do with life? The number one thing that the moon does for the Earth is it creates big tides. Now, for 4 billion years, there was life on the planet, and it was all in the water. There was no life on land. And it had to make its way out of the water onto the land to become you and me. And how did that happen? Well, every time you have a low tide, you pull the water away and you strand things up on the rocks. And for billions of years, anything that got stranded on the rocks died. Didn't make it till the next high tide. But eventually, as that water got pulled away, some things got stranded on the rocks, and those things eventually became all the life on the land. What this tells us is that had the Earth not had that collision early on, and we didn't have a moon, and we didn't have the tides, chances are the Earth would have lots of life, and it would all still be in the ocean. So to have life like ours, we also need to have a moon to create the tides. And just a reminder, we're not supposed to have the moon. So that tells you something about trying to find life like us elsewhere in the universe. Some other things happen on the planet that are very, very significant. So this graph shows you the number of basically broad kinds of life, categories of life, over the history of the Earth. And life formed pretty early, and we got lots and lots of kinds, and then 57% of all of those kinds of life disappeared. After that, new kinds of life showed up, including something called cyanobacteria. And they took the carbon dioxide in our atmosphere and made sugars, and in that process converted the atmosphere into oxygen. And that's a very important process for us to exist. But in that process, it also caused half of all the other life on the planet to die off. Well, we then went for quite a while where things were pretty stable, quite a few kinds of life hanging around. And then in what we now call Siberia, a lot of lava erupted onto the surface, put a lot of sulfur in the atmosphere, changed the climate, and 5/6 of all the life on the planet disappeared, 84% of it. So just think about that. 5/6 of all the life on the planet gets wiped out. We then go for an extremely long period of time, 250 million years, where we have more and more new kinds of life. They're here for a very long time. They're very successful. And then an asteroid hits the planet and wipes them out. That's the age of the dinosaurs. And that wiped out 47% of the life on Earth. And with that cleaned off, new life shows up on the planet faster than ever before until, lo and behold, we show up. Modern humans, Homo sapiens, have been on the planet 50 to 100,000 years. anything the family Homo, Homo erectus, Homo habilis, all of our Neanderthal and hominid type ancestors have only been here 1 to 2 million years. This is a 4.5 billion year scale. We're a very recent addition, but our kind of life is only here because life on Earth has been wiped out 5 times beforehand. So think about all the other kinds of life that have been here. Dinosaurs for 250 million. You're much more likely to find dinosaurs than you are to find humans. Now, as we look for life in the universe, we have a couple of key ways of doing that. One of them is something called SETI. So we are listening for radio signals coming from planets around other stars. The assumption being that if you do have life that's like ours, that is technological life, and they are watching I Love Lucy episodes, maybe we can listen in on those. So there's a program to listen in for radio signals coming from planets all over. Looking for planets is a major effort. We have several ways of finding them. One of them is measuring the tiny little wobbles in stars that are created by the gravity of planets as they go around. And the Keck telescope you see there at the bottom center has been used many times and found many planets that way. But the king of finding planets is a spacecraft called Kepler, the upper right. And what it does, and it did for several years, was stare at one small area of sky and measure the brightness of all the stars in that area. And as planets pass in front of the stars, those stars appear to be a little dimmer because a little bit of the light is blocked. And Kepler found a lot of planets. This gives you an idea of conceptually just the first few hundred that it found. It found 4,000 planets out there. Now, as it's looking, of course, the bigger the planet, the easier it is to find because it either causes the star to wobble more or it blocks more of the light. And so we tend to find bigger planets more often than smaller planets. And so we tend to find things that are more Jupiter-like or Neptune-like than around Earth-like, because actually, if you look at this to scale, the Earth is only that big compared to Jupiter. So finding Earth-like planets around other stars is still a challenge, and we're still looking for that. Now, right now, while you're breathing in and out, you're breathing oxygen. And oxygen is a key part of you being able to take in food, sugars, combine it with oxygen, break it apart, and extract that energy. But oxygen is not natural in the atmosphere of a planet. Oxygen attacks everything. It binds to things very, very easily. And since carbon and oxygen are the most common things in the universe, beyond the hydrogen and helium, they combine to form carbon dioxide more than anything else. So if we look at bodies in the universe, we look at planets, you're more likely to have a carbon dioxide atmosphere than anything else. And in fact, Mars and Venus here, for example, their atmospheres are basically all carbon dioxide. Now, the thing about carbon dioxide is that when you combine it with water and make sugars, you also release oxygen. So the cyanobacteria did that, and right now bacteria and plants are doing that. And all of our energy ultimately comes from those processes. Carbon dioxide and water are keys to producing the kind of life that we have. If you look at any planet elsewhere in the universe and you see an oxygen atmosphere, you know there needs to be something living there, because only living things, as far as we know, can convert the carbon dioxide into substantial amounts of oxygen. It also says something about how important water is. We think right now that if you're going to look for our kind of life, you need to find places that have water. And that makes some places in our solar system particularly interesting. So to the upper left here is one of the moons of Saturn called Enceladus, and Enceladus is covered with ice. Ice just as you would find in the polar regions here. But heat generated inside of that moon, because of the way it orbits around Saturn, helps melt some of that ice, and there are actually water geysers going all over it. So it's a possibility, since you have liquid water up there, that you could have our kind of life floating around. And indeed, Europa, one of the moons of Jupiter, shown at the bottom here, has a similar process going on. And in fact, we see what we think are organic type compounds floating around on that ice as part of this process. Mars, we have a lot of evidence that there was flowing water on Mars at one point in the past. And so we have rovers going around Mars, this is Curiosity here, looking for organic compounds, looking for the evidence that life might have been there in the past. Now, these are places that we can explore directly because all things considered, they're relatively close. How would we do this around things in the distance? So as Kepler has been out there looking for planets, and we have a new satellite up looking for those now and trying to find Earth-sized planets, the important thing is finding planets that are the right distance away from their stars. In too close and any water would boil away. Too far away, all the water would be frozen. So there's only a short range of distances over which you could have liquid water, and that's nicknamed the habitable zone. And so Kepler 22b is one such planet that's in the habitable zone around its star. And this is a comparison between our solar system and the Kepler 22 system. And there are a handful of planets that have been found that are roughly the size of Earth. They're all a little bit larger, but compared to the Earth, they're not that enormous. And so finding an Earth-type planet, an Earth-sized planet in the habitable zone around another star that clearly shows signs of water would be a really amazing thing. And there's some other systems we found, one called TRAPPIST-1. Its planets go around a star the star itself is relatively cool and red, so the planets are in closer, but it actually has 7 planets that were in the habitable zone of that star. So we're starting to get better at finding planets that might be capable of supporting our kind of life. So that opens up the question, are we alone? And in fact, does it really matter what kinds of life that we find out there? So if you talk about human beings, let's think about our own Earth. Hundreds of millions of different kinds of life have existed on the Earth. Precisely one of them looks like us. There are all sorts of different things out there. There are so many different ways to put carbon compounds together to make things that are living. So from my perspective, it's really hard to believe that if you went to another planet and you found life, that it would look anything like us. It might look like a dinosaur. It might look like a blade of grass. It might look like a virus, for example. And in fact, if we found viruses somewhere else, that would be hard to do because viruses don't breathe the way everything else does. Everything else exchanges gas in some way, and we can detect gases, but viruses don't do that. So are we really a special species? Well, we're unique, and indeed, this may be the only place in the universe that has humans because we're just one of the many ways to put life together. If you visited another planet, I think the chances of finding life somewhere else in the universe are very high. Why? Because we know those life-giving compounds are all over the universe. And there are many places that you could go and find that. There are trillions of galaxies, each with hundreds of billions of stars, and each of those stars has planets. It's very hard to believe this is the only place with life. On the other hand, there are so many different ways you can make life. It's pretty unlikely that you'd find a particular kind of life if you look out there. If you ask people how life is organized on Earth, a lot of them would say that you have a hierarchy that looks like this, that we're the top of the heap and everything else is here for us to take over and use. I think if you look at all the processes that made it possible for our kind of life to be here and all the other kinds of life to be here and the hundreds of millions of different ways you can put things together to have life, you have to rethink that and actually, I think, recognize that there is no hierarchy, that everything here is interconnected, that every bit of life on the planet affects the geology, which affects the water, which affects the atmosphere, which affects the minerals, which affects our lives, that everything is tied together and that there really isn't a hierarchy. We happen to be one of the species here. We happen to have certain characteristics. But everything else out here has unique characteristics as well. Jonas Salk, who invented the polio vaccine, made an important observation. He said, if you removed all the insects from the earth, in 50 years, the rest of life on the planet would end. But if you remove the people from the earth, in 50 years, all the other life will flourish. I think that changes our viewpoint about where we fit in and what's really important here. Albert Einstein pointed out we can't solve problems by using the same kinds of thinking that created them. We need to think differently. We need to have a different viewpoint to really make a difference. There are quite a few books that I think really address this very well. And on our website, which I will cite for you at the end of our talk today, there are links to all of this information so that you can also learn more about these processes, and I hope change the way you think about things and the way you do things. Now, over history, not that long ago, a few hundred years ago, people were very much more connected to the environment and connected to the sky. And there are a lot of reasons that we aren't as connected now, but the biggest one is that you can't see it. 80% of the world's population cannot see the stars. And that's actually a symptom of the problem. The problem is too much light going in the wrong places. And that light actually does a lot more damage than just remove the stars. If you live in a light polluted area, and most of you listening to this right now probably do, you are at greater risk of getting breast or prostate cancer. It contributes to obesity, diabetes, and behavioral issues in adolescence because it affects sleep patterns. It affects plants and animals. Pollination is down as much as 60% in places that are light polluted. And of course, without pollinators, we're not getting our food. So it's a very important thing, even just for us. It affects plants. It affects animals. Over 1 billion birds die each year migrating because they get trapped in the lights of cities. And of course, we lose the night sky. This is the US at night. You have to realize that none of the light you see here is actually lighting anything because you can see it from the satellite that's up above. This is light that's going straight up. It's bad enough that we're making light that's not doing us any good, but we also have to make electricity to power that light. And for every 100 watts of light that you burn for a year, you need to burn 2,000 pounds of coal in a power plant. So ask yourself how many 100-watt bulbs this picture represents, and think of all the pollution that's generated from all of that coal. So we have a whole variety of issues that are a consequence of misuse of light. Here's the Northeast, New England. This is what satellite data looked like in 2012, and here's what it looks like in 2018. Some of that growth is due to growth in population, more stores, more people, more houses, more businesses. But a big part of it is something that should have been a good thing, but is turning out to be a bad thing, is the switch to LED illumination. LEDs are wonderful. They use very little power, they're very inexpensive, they last a long time. They're a great technology, but unfortunately, human beings are greedy, and so since they're so inexpensive, if light is good, more light must be better. And so the lights that go in are too big, too bright, and too blue. So here's an intersection that had the original kinds of LEDs put in, these very bright 4000K LEDs. I'm sure you've seen these all over, and there's a lot of glare. It's extremely bright. There's light going into houses left and right. Not a very good thing at all. This one intersection you can see was improved when the light fixtures were replaced with a different kind of LED. Just by changing the LED color, lo and behold, you get better illumination, less glare, and actually less power use as well. When you look at lighting everywhere, you need fixturing that only sends light down. You need light where you need it. So this is a display in a local Lowe's. And unfortunately, most of the fixtures here do not send light down. They send light up, they send light around. Very little of the light coming out of those fixtures is actually going to do any good. And most of it is just going to create glare and waste energy. There are a few fixtures here that might be good because you can steer them. So if the person who installs it also points the lights in the right direction, they'd be okay. But if you don't point them in the right direction, they could be just as bad. So in this entire display of all the fixtures here, there are only 4 that actually work with the environment. It's very important that you can look at your homes, your businesses, schools, municipalities, and have the right kind of lighting. With that, it will be safer, healthier, and use a lot less power, and the stars will come back. There's a citizen science program called Globe at Night that I invite you to participate in. Globe at Night has an app, and you can measure the sky brightness. Deliver that data to the Globe at Night site. That data is compiled around the country and around the world. It's a very important program to monitor what is happening with light pollution in the night sky. Please contribute to Globe at Night. It's a very fun thing you can do. You can make measurements at home, at your businesses, when you're on vacation, when you're walking down the street, and provide that to this worldwide program. Last summer, the Washington Post published a map that showed the last places where you can actually see the sky. And most of those places are out west in mountain or desert areas that are not particularly accessible. There's only one place in the eastern 2/3 of the entire country where the sky is actually dark, and that's in northern Maine. And that happens to surround the Appalachian Mountain Club lands up in the northern Maine woods. We are in the process of working with the International Dark Sky Association to protect that region as an international dark sky reserve. Because if we don't protect it, there will be no place in the eastern US where you can actually properly see the stars. It requires that we get surrounding towns and businesses to control their lights in perpetuity. It's not a matter of it being dark now, but we need it to be dark long into the future. Now, there are a lot of things that you can actually do based on the information we've been giving you today. You can look at your businesses and the kinds of products that you make. And for example, the packaging, all the excess plastics and containers and materials, which just produce waste and use up a lot of energy. We don't have to do that. You can look at your businesses and find ways to do things in manners that don't have the impact on the environment. We can look at our food and our food production. Buying local saves a lot of energy, produces better food, keeps you healthier. We can change the lights around our own properties. We can reduce glare, reduce energy use, and improve the environment. We can look at the plantings around our houses. Lawns may look nice, but they're actually not very good for the environment. Whereas if you have native plantings, lo and behold, you can bring the native species back and produce environmental corridors. There are a lot of things that you can do yourself on your own to actually make the world a better place that aren't hard to do, but will actually make a difference. And then you can make a difference on a larger scale. We all vote. You can vote on the basis of what's just important for you or what's important for the world as a whole. And we need to carry this message forward. I'm hoping that the next time you're sitting down with some friends, you can tell them about this and forward a link to this talk and say, hey, we all need to do this because there are 7 billion people on this planet. We need a lot of people to change what they're doing if we're actually going to make the world a better place. I think if everybody could see a sky like this and realize that there are 1 trillion galaxies, each with 100 billion stars, those stars have planets, they're all bathed in life-giving compounds, there is life out there somewhere in the universe. We just happen to be one of the many different ways that you can organize that chemistry to make life. Are we unique? Very possibly. Are we more important than everything else? I don't think so. We need to rethink where we fit in and how we live. There are quite a few organizations that have helped us with our programs. I hope you will take advantage of their offerings and support them. In particular, the Springfield telescope makers hold the Stellafane telescope conference every summer in Springfield, Vermont. It's a great opportunity to look through hundreds of telescopes with thousands of participants in a relatively dark place. Terrific speakers, great information, a wonderful community to be part of. Our programs sponsor undergraduate students who work with us through the summer. We need support for them. We have a GoFundMe campaign. I hope that each of you will make a contribution to that campaign. Every little bit helps. It helps us hire them, pay for their room and board, train them in science communication, and reach lots and lots of people with these important messages. I'll leave you today with these links. We have our program website, mountainsofstars.org. On that site, you can get copies of all of our presentations and materials, links to the organizations we discussed, links to the International Dark Sky Association and Globe at Night, opportunities to participate in all of the work that we do. We have a Facebook page, which is Mountains of Stars. We post up all sorts of environmental and astronomical information there. Please visit that page, like that page, share that page with as many as you can. And feel free to reach out to me personally. Our email is here on this slide and also linked through our website and our Facebook page. Please let me know if we can do presentations or workshops for you or provide you with more information. Thank you very much for listening, and I hope this has changed the way you think about your place in the universe.